We know that if we make an electric field, perhaps we have two positive plates, and we put something between it that is not polar. So let's look at a xenon atom or something like that. We know that the negative part of the electron cloud will be attracted to the positive plate, and the nucleus will be attracted to the positive plate. So we end up inducing a dipole. And all substances are somewhat polarizable. And we denote that using this equation, saying that the dipole moment that's induced in the molecule is going to be equal to the polarizability times the magnitude of the electric field. We're making an approximation here that this is all linear and that the vectors point in both directions, and furthermore that this is just a single number. In actuality, it's much more complicated because molecules have different polarizability depending upon their orientations with respect to the field. But we're going to use this equation, which means that this is called an average polarizability. Let's look at some trends in molecules' average polarizabilities. First, a word about the units. These are called polarizability volumes because the units are in meters cubed. And so what this is we actually take the real polarizability and divide by 4 pi epsilon naught, and that's what gives us our units of meters cubed. The actual polarizability, for instance, for water would be 1.5 times 4 pi epsilon naught times 10 to the negative 30 meters cubed. So that's the actual polarizability. So you have to multiply by this part times the number in the table. Anyway, let's look at trends. We can see that it really has nothing at all to do with polarity. Okay, so nitrogen, water, nitrogen has a slightly higher polarizability. It really has to do with the number of electrons, especially electrons that are in outer shells that are more evenly shoved around by the electric field. And so bigger atoms tend to be much more polarizable than smaller atoms. And so chlorine has the same number of atoms as nitrogen, but it's lower down the periodic table, has a higher radius, a larger radius, and so that makes it much more polarizable. Also, if we just have more atoms, we can get a bigger polarizability. Notice carbon tetrafluoride down here. So now we've got 5 atoms, so certainly a pretty good sized molecule, and yet its polarizability is not all that high. Why? The reason for this is that fluorine is so electronegative it tends to sort of hog the electrons. And so electrons in fluorocarbons are just not mobile. They're not able to be, electron clouds are not able to be distorted that much because they're stuck to each individual fluorine atom. So polarizabilities of fluorocarbons are low, and we're going to see that plays out in having much lower IMFs than hydrocarbons, which is why we'll see later this leads to the fluorocarbons having very low surface energies.